Okay, thank you very much. As you can see, this is joint work of two Christians, and it started many years ago in Nagoya, FPSAC, in the hotel lobby. And when Christian asked me, we'll say it in English, do you want to prove another cyclic sieving phenomenon? And I, of course, sure, why not? Right, and of course, he explained to me what this is about, and therefore I have to explain you now, before I can continue what this is about. And it's about non-crossing partitions, and actually this M-realized generalization, m-divisible non-crossing partitions, and associated with reflection groups, as we have seen in the talk of Christian Stumpf, although my presentation will be slightly different. So this page should be very familiar. It's about length with respect to transpositions. In the symmetric group, or in general, it's the reflection length in reflection groups. So it is the shortest way to decompose an element as a product of conjugates of the reflections. Simple reflections. Right, and the absolute order then is defined via the absolute length, namely one element is less than or equal to another, if and only if the lengths add up. So you have length of u, length of w, and this is, so to speak, the difference between the two, and then this should add up. Right, and many years ago, Drew Armstrong defined m-divisible non-crossing partitions associated with reflection groups. And so Christian Stumpf told you these are chains in the non-crossing partition lattice. I present it in an equivalent way as m+1 tuples of elements of the reflection group, such that the product gives the Coxite element C. So you fix the Coxite element in the very beginning. So in principle, these non-crossing partitions depend on this element C. But since I will look at this as a partial ordered set, it doesn't matter which Coxite element you choose. Right, and again, the length should add up. Then if this m is equal 1, then one is reduced to the usual non-crossing partitions for a reflection group. So I usually want to have something which is more concrete, and there is a translation into ordinary non-crossing partitions, and it works as follows. So again, this is due to Armstrong. I give any, so I don't give you the general definition, I explain you the translation via an example. I choose A6, which is the symmetric group on 7 elements, and my choice of W0, W1, and so on, you can see. And indeed, if you take the product of these 4 permutations, then you get 1, 2, 3, 4, 5, 6, 7, the long cycle. 1, 2, 3, 4, 5, 6, 7, which usually is chosen as the canonical long cycle. And also the lengths add up as they should. So this is an W0, W1, W2, W3 is an element of the 3-divisible non-crossing partitions. And what we do now is we blow up, we forget about W0, we blow up W1, W2, W3, which means that we multiply all elements by m, in this case by 3. So I start with the last one. The last one, 1, 2, 1, 2, 6. I get 3, 6, 18. Okay. For the element before, what do I get? 1, 7 times 3, 3, 21, and there I subtract 1, 220. So I multiply this element by 3, I get 9, 18, and I subtract 2. I get these two elements. Then I take the inverses. In front, I put the long element now in S3 times 7, 1. I multiply these permutations and I get something. And it turns out that this can again, so this is in cycle notation, it can be again seen as a non-crossing partitions if you put it on the cycle. For example, you have the block 1, 2, 21, 3, 19, 20, and here it is. 1, 2, 21, and so on. So this is the result. And what you can see here, and what you could also see here, all the block sizes are divisible by 3. This construction gives you a non-crossing partition. All block sizes are divisible by m. Okay, very good. Drew has a similar construction for type B, and then you get again non-crossing partitions. All block sizes divisible by B, and in addition, the picture is invariant under rotation by 180 degrees. And I came up with variant for type D, and then you get partitions on an analogous. Namely, on the outer side, you have 1, 2 up to n minus 1 times n, and the negatives. And on the inner cycle, you have the rest of the entries, and then you get partitions where, again, the block sizes are divisible by m. And there are certain rules concerning the inner cycle, which are a bit technical, but which I won't make it. Yeah. Yes. You mean this here? Yes, it's not very complicated in my opinion. Right, and again, the picture has to be invariant under rotation by 180 degrees. Okay, so, but you will not remember, but I had positive non-crossing partitions. So what are these? So they come from work by Juan Reiten and Hugh Thomas, who wrote about non-crossing partitions and M clusters. And there they constructed a bijection between the generalized clusters of cluster complex of Fominant reading and m-divisible non-crossing partitions. So I should point out that these M clusters, these generalized clusters, are counted by this number here, which we have not seen so far. So these are the positive M generalized cut-around numbers. But we have seen the ingredients already in Christian's talk. The DI, these are the degrees of the reflection group, and H is the largest degree, the Coxeter number. Right, and so Gunnar, Reiten, and Thomas, they declare, for these clusters, positive makes a sense. Namely, the clusters, they are simply sets of simple reflections. Some of them positive, some of them negative. And if you have no negative reflections in this set, you can say this is positive. And then they say, okay, whatever the image is under their bijection, these are the positive M generalized non-crossing partitions. Right. Of course, this is very nice and very good, but what does it mean within the m-divisible non-crossing partitions? There's also a definition. If you want, you can characterize what you get. And the characterization is that you get all these m tuples such that the product of the first m1 is not contained in any proper standard parabolic subgroup of W. So this is a definition. Of course, it's not easy to verify and to work with in the first place. Okay, here it is again. Obviously, these positive m-divisible non-crossing partitions, they are counted by these same numbers here. And in fact, Burenreiten and Thomas in their paper write, other than that, there do not seem to be enumerative results known for these families, except for this. In the background, why do they write this? Because if you forget about positive, then there are many enumerative results. So you have a result for the total number, you have results for the number of those elements, those m-divisible non-crossing partitions, which have a certain rank. You can go further. When you do the combinatorial translation, you can tell what the block sizes are, and then there's a very nice formula. You can count the number of chains, and you can even put everything together. You can count chains where you predict the ranks and where you predict the block sizes of the least element. So let us see what we can do for the positive non-crossing partition. So as I said, this definition of Burenreiten-Thomas is very abstract and doesn't tell you much. And again, I like combinatorial gadgets, so these pictures, these non-crossing partitions. And therefore, what does it mean for such an m-divisible non-crossing partition to be positive? So you apply Armstrong's map, and then you get some m-divisible non-crossing partitions. What does it mean to be positive? And after some work, you figure out what it means is that 1 and mn are in the same block. This is everything. This is a positive one, so I have marked 1 and mn, so they are in the same block. These are the positive non-crossing partitions. Otherwise, the usual condition block sizes are divisible by m. This is for type A. For type, right, and so we proved several enumerative formulas. This is the total number. Of course, this is a special case of the formula that I have shown. You can count all those. You can count the chains of length L minus 1 of a given length. You can count those which have a given block structure. You can count chains where you predict the ranks of each element and also the block structure of the bottom element. And they are always very nice formulas. This is an analogy to what I have shown you for the case where you forget about positive. Yes? This is correct. For type A, this is this is a way to count them, but in the other types it's more complicated. But yeah, that's right. Yeah, but if you have even results where you give the block structure Actually, you have more general results than right. If m is equal to 1, then you have results on the block structure, and from there you can extract it. Yeah, it's correct. But as I say, for the other types, this is not so simple. I think this is the one with things where you predict the rank sizes and block structure of bottom element. Anyhow, so type B. So again, you apply Armstrong's map, now in type B, and you try to figure out what it means for a partition to be positive. And here it turns out that the condition is that the block of 1 must contain a negative element. So this is an example. It's, in this case, it's mn minus mn, so I write bar for minus something. But it need not be, 1 need not be connected with 12 bar, it could also be connected with 6 bar or something. Otherwise, same conditions, block size is divisible by m, and rotational symmetry, 180-degree rotational symmetry. Again, we proved the numerative results. Total number is, of course, a special case again of the previous formula. Then there's one special thing, such m-divisible non-crossing partitions. They can have a big block in the middle, which is usually called the zero block. And so you can count all these m-divisible positive, m-divisible non-crossing partitions where you fix the size of the zero block, the central block, and you can even, again, give the block sizes. And then there's a very nice enumerative formula for the positive m-divisible non-crossing partitions in type B, where you give the block sizes. But here we don't have results on chain enumeration. We did not really check whether there are nice results. I tend to expect them, but our techniques don't allow to assess this. Type D. So now one has to apply this map to the non-crossing partitions on the analogous, and already there things have been more complicated. And but the additional complication when you put in positive is only again this condition that 1 must be in an element with a negative element on the outer circle. So I say here the predecessor of 1 in its block is a negative element on the outer circle. Again, here's an example. 1 and the predecessor of 1 is minus 15, but it need not be minus 15. It could also be minus 11. Otherwise, conditions are the same. Every block size is divisible by m, symmetry under rotation by 180 degrees. So here things become somewhat complicated, so we just proved 2 results. The total number, which again is just a special case of the general formula, and then number of positive m-divisible non-crossing partitions in type D, where all block sizes are equal to m. Gives you that formula. Right, so now I've discussed all the combinatorial realizations of these positive m-divisible non-crossing partitions. for type A, type B, type D. And then I come to this other thing in my title, cyclic sieving. Right, so this was, so to speak, invented in 2004. And since then, it has developed into a fundamental principle in combinatorial enumeration, namely, whatever family of combinatorial objects you have, it satisfies cyclic sieving. Maybe I first explain what cyclic sieving is. Invented by Reiner, Stanton, and White. So what you need is a family of combinatorial objects, M. You need a cyclic group that is acting on this set. And you need a polynomial. So the cyclic group is C. The polynomial is P of Q. And then it says this triple set group, cyclic group, polynomial exhibits the cyclic sieving phenomenon if you can compute the number of elements that are fixed under a given element of the cyclic group by evaluating the polynomial at the, so to speak, corresponding root of unity. That is, so if you want to know which elements are invariant, under G is the generator of the cyclic group, under G to the P, then you compute the polynomial at the primitive Pth root of unity, primitive cardinality of C root of unity, and raise this to the P. This is what you find here. Very simple example. In principle, but if the cyclic sieving phenomenon is satisfied, then it will give you that number. Here's a very simple example. You take the element, the subsets of size 2 of 1, 2, 3, up to 4. 6 elements. That is 4, choose 2 elements. I choose as group the one which shifts all the elements. So, for example, the set 1, 2 is mapped to the set 2, 3, and the set 1, 3 is mapped to the set 2, 4. You add 1 to each element of the subset, and the polynomial will be the Q binomial coefficient for choose 2. I write here explicitly, and I claim this satisfies the cyclic sieving phenomenon. Let's see. So the elements that are fixed under the identity, and these are all of them, that is 6. And of course, if you put Q equals 1 in the polynomial, you get 6. Easy enough. Second, do you see any of these sets that are fixed by this shift? Certainly not. This is impossible. So we should get 0. And what we have to insert is the first power of the fourth root of unity. The fourth root of unity is I. So we should compute P of I. And do it, and you see you get 0. Then G squared. Now you shift by 2. Then there are 2 sets which are invariant, namely 1, 3 is invariant, and 2, 4 is invariant. So you should get 2 if you plug in I squared, minus 1. Okay, so you plug in minus 1 and you see that you get 2. Then the third case is analogous to the right, so this satisfies the cyclic sieving phenomenon. Right, and so whatever, it seems, whatever combinatorial objects you choose, they satisfy the cyclic sieving phenomenon. And obviously there's a trivial corollary to this. The positive m-divisible non-crossing partitions satisfy the cyclic sieving phenomenon. Obviously at this point this is a joke, but right, because we need a cyclic group and a polynomial. Okay, so where's the cyclic group? So let me go back to m-divisible non-crossing partitions without positive. There is a group action known. So I think you defined it, I have forgotten. Yeah, right. I think the thesis to define it. So here it is. You take such an m+1 tuple, and what you do is essentially that you rotate the W's. So you see that the W's are shifted one place to the right. And then, of course, Wm drops out on the right and has to go to the beginning. And it does go to the beginning, but then there is this, how to phrase it, and you see the first component and also the second component, they are slightly perturbed. But yeah, so this is the definition. And you can convince yourself, first of all, it is again a non-crossing partitions. That is the product gives a coxate element C. And second, after MH applications, you come back. I did not tell you, but here are the M-merlized Krattenthaler numbers. So there's just a tiny difference to the positive ones. There's no -2. But now the question is, which polynomial do you choose? It is this polynomial. So the thing in bracket is the usual thing. Okay. Okay, I've chosen a different convention here. It doesn't change anything. Anyhow, and with Thomas Müller, I proved that this triple satisfies the cyclic sieving phenomenon. And there's a second cyclic sieving phenomenon when you fix the W0 to identity, then the same map with slightly different polynomials. So m is replaced by m-1, also satisfies the cyclic sieving phenomenon. Very good, so we have a map. But unfortunately, if you apply these two positive m-divisible non-crossing partitions, then you don't get positive. You don't get always positive ones. Okay, but then maybe we should modify this. Here is the modification. It has a very similar look, except that there is a kind of decomposition of the n-first component. So Wm-1 is decomposed into a left part and a right part. And if you do this, then you can write down this decomposition. So the problem is, what is the left and the right part? Here's the definition. It's obvious that I will not go through this because there is no chance that you will understand or grasp this within 1 minute. So, but the point really is there is a definition. And then this rotation, as it will turn out, kind of rotation is an action. Back. So yeah, so this is now our action on the positive m-divisible non-crossing partitions. Which polynomial do we choose? Same principle, you take the number and then put brackets around, and this is the polynomial. Of course, this has no right to really be a polynomial, but you can prove it is a polynomial. And it even has non-negative coefficients. And so now we come back to the hotel lobby. So this is what Christian Stumpf explained me in this hotel lobby, that he thinks that the m-divisible non-crossing partitions with this action and this polynomial, they satisfy the cyclic sieving phenomenon. And there's again a second one where W0 is fixed to the identity. Again, of course, also have to modify the polynomial slightly. Okay, we are back in the hotel lobby. So you want to point out this is a few years ago. So, and the reason is that this turned out to be a bit more complicated than we thought. But 150 pages later, I can announce that we have proved it. So these are theorems now. And let me say a few more words about this. Right, so first thing, we don't have a nice proof. 150 pages cannot be a nice proof. Our proof is by case-by-case analysis, as you often do when you do cyclic sieving, because insightful proofs, they are really very difficult. Yes? When you go to the combinatorial realization, it means that all block sizes are equal to m. Because W0 gives you the block sizes of the image under this combinatorial realization. And so if W0 is the identity, then all cycles of the identity have length 1. And therefore, the block sizes are these ones multiplied by m. So m, all m. This holds more generally. If you have W0 is something, and the cycle lengths are L1, L2, L3, and so on, then the block sizes in the image will be m times L1, m times L2, m times L3, and so on. Right. So here I want to sketch how this action of this bigger definition that I have shown you, how it works in type A. So in most cases, it's just rotation by 1 unit. So whenever rotation by 1 unit doesn't destroy the defining property of the positive m-divisible non-crossing partitions in type A, meaning that 1 and mn are in the same block. If you rotate, and this is still the case, then this is the action. If not, then there's a slight perturbation. So this is schematically. Here, if you would rotate this block by 1 unit, then 1 and mn would not be in the same block anymore. And so what happens is that this block here loses this first element, it becomes this one, and instead grasps this element shifted by 1 unit. This is this one here. And a similar thing is happening with a block that is moved into Mn. Yeah. And this is also the reason. So if you do ordinary rotation, then after Mn steps, you will be back. So here you will be back sooner. After Mn minus 2 actions, you will already be back. Maybe Mn minus 1. Okay, so you remember cyclic sieving is about counting elements that are invariant under group elements. In our case, it means to count elements like go back and put it on. Yeah. No, I'm pressing the wrong buttons, it seems. Yeah, right, yeah. So I will call this a pseudo-rotation, because in many cases it is rotation, in some cases it's a slight modification. Right, and so now we have to determine the elements that are invariant under some power of this rotation. And so here's an example. If you look from very far, then it looks as if you need 4 90-degree rotations until you are back. Essentially, this is the case. So it's about the power of Mn minus 1 or minus 2 over 4 of this action. Then you map it to itself. You can see that the central block is a bit funny. It's not really symmetric, but this is because we have this funny action. In any case, we have a characterization, how to build those, and then we can do the enumeration. And this goes up to enumeration of elements where you predict the block sizes. This is the corresponding result. And from here, you can derive many other results. And this leads to several cyclic sieving phenomena. You have one for all the m-divisible non-crossing partitions of type A. You have one for those where all the block sizes are equal to m. You have one for those elements which are at a certain rank, or equivalently, which have a given number of blocks. And you have also one where you fix the block sizes, and then there's also a cyclic sieving phenomenon. The only thing that changes is the polynomial, and of course the set. Okay, this is type A, type B. Again, you apply Armstrong's map and try to figure out what this rotation is. In most cases, when the defining condition, and now the defining condition is that 1 is together with a negative element in a block. When this condition is not destroyed, then it's ordinary rotation. And if it would be destroyed, this is one example here, then there is again this kind of modification, very similar to the previous one. This partition is moved to the right, but then grasps an element from the next block, so it becomes this one here. No, that's not true. It becomes that one here, and the central block grasps one element from there, but loses it at the same time. And with this analysis, one can again determine, characterize which ones are invariant. So they are very simply built, and this is an example. And with this, again, you can compute the number of these non-crossing partitions where you fix the block sizes and that which are invariant under a certain power of the generator of this group. Somewhere there is where is it? Here it is. Here's the generator, and it's raised to the mn-1 over some r. This is the way that we present it, because then the formula is easier to write down. So it was mn-2 for type A. In type B, the order is mn-1. And with this, you have again the cyclic sieving phenomenon for all the m-divisible non-crossing partitions positive in type B, for those where all block sizes are equal to n, for those where you fix the number of blocks, and for those where you fix all the block sizes. And finally, type D, same story. You do the translation. Now it's even more complicated. You have several cases depending on whether the central block exists and contains all elements of the inner circle or not. The rotation on the outside circle goes forward. The rotation on the inside circle goes in the backward direction. Anyhow, so here's another example. And another one. And when you characterize those which are rotationally invariant, then there are three constructions that we have. And the only enumerative results that we determined were for all non-crossing partitions, or only for those where all block sizes are equal to m. Probably you can do a bit more, but it becomes very complicated to computations. And so we have two results, one for all non-crossing partitions in type D, one for those which are where the blocks have all size m. So how do we prove the results? Generating functions. So we do the combinatorial decompositions of these objects, and the Lagrange inversion formula is very important. Right, there were also the exceptional groups. And so usually the problems with exceptional groups are finite problems. So the only thing is that the computer should be big enough, but here this is not a finite problem, because there's a parameter m. But still, we were able to reduce the problem to finite problems, and then, of course, the computer came into the game and things were verified. And this was it. Thank you very much.